All right, so we are discussing. We just walked into this lesson. I asked the question, "What's a capacitor?" We're struggling a little bit. I went back to what is a battery. Am I wrong? No. So don't get mad about something that's 110% accurate. Okay, don't get wow about something that is 110% accurate. One side's negative, one side's positive. A battery is a permanent separation of charge, such that if you compare those two spots, if you touch those two spots, what's going to happen? I've got negative on one side, positive the other. I just attached both sides to the wire. What's going to happen?
Charges getting separated.
No, we already talked about that. The battery has already separated the charges. Now I've connected the battery with a wire. What's going to happen?
Why is it going to get hot?
You're missing what I'm talking about. You're not wrong in a basic sense, but not what we're looking for here. What's going to happen?
The charge is traveling.
Thank you. The charges are going to travel. Which charges move?
The electrons, the negatives.
The negatives. The negatives are going to be repelled from the negatives and travel over to the positives. Or we would say that there is a potential difference between these two spots or an electric field going this way. So in all capacities, this should see that the negatives move from one side to the other. Now we can talk about the forces on them and the umph and the push, or if we have the potential difference, which we do for like a standard battery, a lettered battery, 1.5 volts, what does that 1.5 volts tell you?
No.
Not newtons.
Joules?
Joules per coulomb. There is that much energy that comes out from 1 coulomb that travels from this side to that side. So, point being, voltage, energy, all of this is to do and explain what's going to happen, or the basic sense of, again, going all the way back to the beginning of, what do negatives do to other negatives? Repel. What do positives do to negatives? Essentially, we're just doing that exact same work. What we shared with on Friday is that, hey, this spot right here has a high voltage. This spot right here has a low voltage. We discussed this the other day, so just a quick review. Which direction is electric field? From high to low. So you would expect a positive charge to go from high voltage to low voltage. You'd expect a negative charge to do the opposite. And the most important thing is if you know the numbers, like if I know that this spot here is 20 volts and that spot there is 40 volts, I know that the potential difference is 10 volts and that a coulomb of charge will get a certain amount of energy. Yes? And we have been equating this exact same idea to a empty hill. The empty hill being, I can look at an empty hill and I don't see no energy. No energy at all is passing through that empty hill. Okay? No energy is passing through this potential difference until
Something falls down
there is a child named Coulomb that rolls down the hill. So there is a coulomb of charge that goes through that potential difference. And if these are the potential differences of both of them, this coulomb of charge just picked up 10 joules, and this child just picked up 10 joules of energy over here. Okay? The value of talking potential difference is you don't have to know how many kids, how many coulombs are running down your hill. You don't have to know how many charges going through there. Like, if you'll remember, how many charges did it take to talk energy? How many charges does it take to produce a force? Two. How many charges does it take to create an electric field? One. How many charges does it take to do energy? 2. Back to 2. Energy. Energy being KQQ over R. Okay? So if the battery company wanted to use energy instead of potential difference, they would have to know absolutely everything that their battery was going to get plugged into, and they would have to tell them, like, okay, let's say you're a customer, it would be, hey, if you plug the battery into this, there's this much energy. If you plug the battery into this uses a different amount of charge, so it's this much energy. If you plug, there'd be a giant scroll of, depending on what object you are plugging this into? Are you plugging it into a toy car? Are you plugging it into a calculator? Are you plugging it into a excuse me, smoke detector? Are you plugging, what piece of electronics are you plugging it into? There should be a giant scroll of, if you plug it in here, use this much energy, or this much energy, or this much energy, or they can tell you exactly how much energy per coulomb that's going through that, in which case all you need to know in order to know how much energy is actually being used is the amount of coulombs. Does that make sense?
Yeah.
Okay. So the purpose of a battery is to set up a potential difference so we can measure how much energy per coulomb is going from one side to the other. Right? So that's the battery. Let's go back up to the first question of today. What the heck is a capacitor? Well, it's these two metal plates. Now, what does the capacitor do? Or what will happen to these plates when plugged in next to a battery? It's not what they do. I mean, you're sort of not wrong, but also they purposely are held at a distance. They don't really, that's not the point.
They hold charge.
They hold, well, sort of. Let's break this down easier. What will happen right now? I've hooked up a battery to these plates. What's going to happen? These plates started off just normal metal plates.
They're going to be charged.
What's that?
They're going to get charged.
This side is negative, so negatives are going to push on over here. Okay? What's going to happen over here? Positives are going to, well, negatives are going to get pulled away, right? Making positive plate over there. Okay? Now, if I look at this same picture from the side, that's going to keep happening until when? No. Yes.
Do those arrows represent the
Electric field.
Until the charge is equal to the battery.
Till the, not the charge, till the voltage is equal to that of the battery. Remember, the voltage across here is 1.5. Why would we get a potential difference? Because we have a separation of charge, right? This represents the push, the oomph, the amount of energy, the empty hill. Think of it like this. Okay, if I go back to my analogy of the empty hill, here's a battery, okay, in which case there is a motor, and this motor is putting more children on top of the hill, right? It's like separating, it's continuously separating the charge. It's continuously lifting these kids up the hill and coming back over here. Now, a capacitor is, as we mentioned the other day, like a hill made of kids. So this kid rolls down the hill and starts here. And then the next kid rolls down the hill and comes right here. And the next kid rolls down the hill. Okay? When are you going to stop? When are you not going to be able to put any more kids on top of this hill of kids? Whenever they are equal. In other words, whenever the potential difference, whenever the push onto this hill is the exact same as the push coming back. Does that make sense? So, when this potential difference between this and this potential difference here are equal and opposite. Okay? In other words, one thing you can think of is like, wait, why are there two numbers here? This is the potential difference of the battery. That is staying at 1.5 because the battery is continuously separating. As you come over here, we got more separation. What's happening to this number? This number is starting off at, what's the potential difference of two neutral plates? 0. So as you separate more and more charge, this number goes up, this number goes up, this number goes up, this number goes up until it's pushing back just as hard. Now, these positives, so these positives here, we're pulling on the negative, like right in the middle. Now that it's equal, what are these positives doing? They're pulling back an equal amount. So how much is this going to move? It isn't. Same thing over here. Now, these negatives have been pushing more negatives on here. But now, these negatives that are pushing them this way, what are these negatives doing in the plate? Pushing it the opposite way, a same amount, so that will there be any more? No. Good. So, a capacitor is two metal plates. For the purpose of separating charge, well, I'm sorry, not for the purpose of, to separate charge in order, what is their purpose? When do we use capacitors versus a battery? What was the application we talked about? When you need a large amount of energy very, very quickly and temporarily. So we talked about this in the form of a defibrillator, okay? We talked about this in the form of a camera. We talked about this, literally every piece of electronics in some way, shape, or form is going to use it. This giant TV right here actually operates under an amount of energy that's just fine when it goes. But if I turn it off, how is the amount of energy to start it up compared to the amount that it's going to take to run it? It's going to be a lot more. So what is the way to deliver a large amount of energy in a temporary amount? This thing has capacitors. If these capacitors burn up and it can't put out that energy, this thing doesn't turn on anymore. As a matter of fact, if you ever hear like a loud pop, or you ever hear a lot of energy, and then your thing won't turn on anymore, chances are good you just blew a capacitor. Okay. Yeah, there's certainly going to be smoke because it was a lot of heat and all that sort of fun jazz. But that's what the purpose of a capacitor is for. Now, a quick rundown of 3 equations that are important. Capacitance. Capacitance is a measurement of how good it is at storing charge per voltage, but that's not its point. The point is just some of the capacitor. What are the units of a capacitor? If you just look at this equation, what are the units? Coulombs per volt. But as we discussed, what is a one coulomb per 1 volt equal to? 1 farad. So if you see like over there, that said 1,200 microfarads, that's the same thing as 1.2 millifarads, which essentially means you store 1.2 millicoulombs for 1 volt.
What did you say? It's a measurement.
What's that?
What did you say? Capacitance?
It's a measurement of how well a capacitor stores charge per certain amount of volt. And the equation, okay, I mentioned this the other day, I'll say it again. People screw this equation up all the time because I say to them, hey, I take that blue capacitor right there and I hook it up to this 12-volt battery over here, okay? And it produces a certain amount of charge. And capacitance is that 1.2 millifarad. And I'm just going to get charged by taking C times delta V, just rearranging this equation. There's capacitance. I plug in a 12-volt battery, and I end up with what? 14.4 millicoulombs in that particular case. Okay? And I then tell people, like, okay, you hook up a new battery. So this guy right here, well, I said 12, it's not, it doesn't matter. Okay? Then I hook up a 1.5 volt battery. Let's say I hook up a couple of them. So I have 3. And here's what people do all the time, and it drives me nuts. They take this amount of charge, and they put it here, and they go, oh, that's 3 volts. And they go, oh, the capacitance must change. No. Why would that make sense? Why was this able to store this much amount of charge? It was able to store that because the battery was pushing crazy hard. If the battery is 1/4 as good, if instead of 12 volts, it's 3 volts now, okay, then it is not capacitance that is going to change. What is going to change in that process? How much charge you're going to store on that particular guy right there. So our first equation, capacitance, or just review. Then we have how to make a good capacitor, and we talked about this in a couple ways. There's epsilon naught, that's a constant. First thing you can do is increase the area. By increasing the area, you create more space for that charge to spread out, and you can store more and more and more charge. Another way to look at it, though, is this. By increasing this area, what you do is you lower charge density. And if you'll remember, charge density was a direct effect of the electric field, or proportional to the electric field. Charge density goes down, electric field is going to go down. If electric field just went down, then voltage, actually, this voltage right here, VED, at the same distance, if E just decreased, the voltage just decreased. And if you're not pushing back as hard, well, then you should be able to store more charge until, once again, the voltages match up like they're supposed to. Then the next thing we discussed was, oops, should use the same color in this case. Distance, because you're right, they do attract each other. Now, not significantly so much that you would ever see the two plates move towards each other, but significant enough to affect the charge on the other plate. Meaning, that's negative because of being hooked up to the negative part of the battery, right? The negatives here are pushing the negatives that way. But what's this positive doing to the negative? Attracting them. So if I make them closer, it's going to pull more negatives onto that particular plate by making that closer. Final thing we discussed, and probably the trickiest one to understand, is a dielectric. Okay? The dielectric is measured with, as we typically do, a constant, and this one is called kappa. Okay? Kappa for air, or actually kappa for a vacuum is just 1 by definition. Okay? Kappa for air is like 1.00001. So if it doesn't say a dielectric or it assumes air, then you can just assume that kappa is 1, and you can leave it. And the reason it works is twofold. The main reason it works is the fact that it is an insulator, and therefore an insulator in an electric field will polarize. Oops. And then I remember thinking this when I was first going through this, like, wait, aren't these negatives right here just going to come over to the positives and touch them and move through? And the answer is no, because it's an insulator. It's held on to those negatives so well that they're not going to bounce through. So, and with them being closer now, then it can attract even, in this case, this can push even more negatives away, making that more positives, and attract even more negatives on, making that more negative, meaning you're storing even more charge. So the 3 ways to change a capacitor are increase area, increase distance, and then change the dielectric in the center. The second reason, by the way, why the dielectric works is the fact that it's an insulator means you can technically make that smaller and smaller and smaller and smaller. So the proper way to make a capacitor, let's see if I actually have this. I have an old PowerPoint that I made for Physics 1 when we were still doing electricity in there. Let's see here, in class. Where's it at? Oh, darn it. I think it's this. I think it's this one. Is this it? This is not it. Oh, it's this one. It's definitely this one. Okay. So I actually, here, let's slideshow this. I actually took apart a capacitor 1 year to try to show what is specifically inside. And once again, you'll notice this cylindrical shape. Okay, you take it off, there's actually a metal surrounding it so that no excess charge can get in there, only being charged by these 2 particular leads right now. You'll notice these 2 leads are surrounded by a fabric. Apologize, the camera, the pictures aren't perfect. And if you actually, it's kind of hard to see here, but look again, okay, these are the 2 metal plates that are right next to each other, and this is the dielectric, this piece of paper covered in oil, making them super close together. And you see right here, just like I was showing them, this first equation right here is your equation for how to create capacitance. But once a capacitor is created, once it's in its packaging, once you're looking at it over there, you can't control this anymore. Capacitance is set for these things. So when you come over here to these 2 sides, you got to understand, like this. If I said, how do you change the voltage of a battery? Hopefully you would go, no, you just do a different battery, right? Or you do more batteries. So it's the same thing with a capacitor. How do you change the capacitance of a capacitor? No, you don't. Once it is made, you can put you don't change the capacitance. You either use a different capacitor or transition. You use more capacitors. All right, so let's talk about that, because that is the next conversation. So what happens when we start doing, what's the easier one? What if I have, okay, actually, I'm going to take a quick aside. Let's go here. Let's come right down here. Like I said, I told you, I was not a big fan of how they positioned some of these things. So here are capacitors, like we talked about, blah, blah, blah. Here's a capacitor with a dielectric. Like we said, it's two metal plates. You fold it all up, you Swiss roll that beast, and that's why it ends up being a cylinder. There's a table. Swiss roll that beast. Yeah, kappa. There. I mean, you're gonna have a table full of them, or it's gonna tell you what it is. Let's go back to this though. Oh, we talked about energy too, but I'll come back and hit that as well. All right, this is what I wanted.
Yes, please. There's like 5 or 6.
Okay, so these symbols right here, they simply represent some basic shapes that you're going to see in here. So I don't have to, excuse me, write and draw all of these things basically. A capacitor, one of those, is seen as two flat plates, kind of makes sense. A battery or any voltage source like the wall or bat represents this right here. So a resistor is just the squiggly line. Light bulbs are all this, but also you're going to see me do this from time to time because a light bulb is actually literally just a resistor. So if you see a resistor inside of a circle, that tells you it's a light bulb. So earlier I was drawing like a battery to a plate of a capacitor. Now what I will draw instead is this. You can see obviously that's a lot quicker, but you have to be able to determine what these things are. A couple of important things. The large side of a battery is the positive side of the battery, or you could also see that as the high potential of the battery. If you'd like to draw the analogy, the large side is the tall part of the hill. A capacitor obviously doesn't naturally have a positive side because you draw the lines even. So there are some textbooks that actually draw it like this instead. The curved line is just to distinguish between the two, and the non-curved side is the side that's positive. Although if you are looking at this from our perspective here, you should see that the right side is positive because it's connected with the side of the battery that is also positive. So then what if I start using multiple capacitors? Okay, let's discuss an important couple set of vocabulary for starters. This is known as parallel. Now, when you're drawing a drawing, a lot of times you will draw them in a box shape. It doesn't have to be in that shape, but because of that, the box can be seen, like you can literally think about them in terms of math as parallel. That's not 100% correct. For example, let me see your eyes real quick. This is also in parallel with each other because parallel in electricity does not mean the same as parallel in terms of math. Parallel basically means simple things. A simple thing. Multiple paths. One item on each. I say one item because you can say parallel for a lot of different types of electronics. This is two capacitors in parallel. This is two resistors in parallel. Okay, now let's talk about how we understand this particular relationship moving forward. Okay, the things that we need to discuss here are, oh gosh, how do I do this one? So I always struggle with this one because I'm much more familiar with the resistor part of things, because we don't usually do this particular setup in AP1, which we have to in AP2. I'm also going to go back right over here and do this one. Okay. So let's think about what's going to happen here to help us out. What's going to happen is, once again, these plates over here are going to be negative, right? Okay, I'm going to have negative going here, and I'm going to have negative going there. Okay, when would these stop getting charged?
And the voltage equals that of the battery.
Now, so the important thing to note here is I'm going to call this capacitor 1 and this capacitor 2. Okay, and I'm going to call this voltage total. Okay, so there will be a voltage for capacitor 1 and capacitor 2. Think of this is not what would actually happen, but think of it charging like this. If these negatives could somehow manage to only go down one path until it was stopped, you would imagine that this C2 here would stop the moment it's at the same voltage as the total. Yes? Then there would be this option over here. So would the charge still go? Yeah, the charge is not going to go down this path anymore, but it would still go up here. Does that make sense? Like, this being, like, again, this is not what would happen. If these both started off as neutral, you get more negative, more negative, more negative, while object coming off positive, 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 and then eventually it's going to be fully charged when VT equals V2. Does that make sense?
Can you restate? What is V2?
V2 would be the voltage of C2.
Oh.
That's why I'm just trying to line them up. Okay? The V2 is the voltage on this capacitor. In other words, what I simply said there is this will stop charging when it pushes back as hard as this is pushing on. Okay? And same thing is true up here. So it will be fully charged, and all of those will be equal to each other. Now, think about this naturally. What should happen to the total amount of charge? Should more charge be stored? In total, across, I've got two capacitors as opposed to one capacitor.
Yes.
This capacitance right here, this C, is Q delta V. Yes? I just stored this capacitor and I used, let's say I'm just going to use a 10-volt battery for the sake of simplicity here. There's a certain amount of charge stored on that capacitor. Yes? Will there also be charge stored up here? Yes. So that would be charge 1, and that would be charge 2. Yes? So the total amount of charge stored is equal to Q1 plus Q2. Now what we need to do is we need to look at what effect that's going to have on capacitance. What we want to be able to do is we want to be able to take that guy right there and start to break it down and go, what could I do? What could I replace those two capacitors with? How could I replace them with another capacitor and have and get the same type of effect? Okay, and the idea here being that we would replace these two. That, like, how could we make it so it's two capacitors, but it's equal to one capacitor over here? This capacitor would be known as capacitance equivalent.
You would have the capacitances together.
What's that? Would you say, what's your idea? Like, why would you add them together?
Because if you're adding the Q's and changing V doesn't change, then.
So the way to look at it is this. Okay, you're 100% right, but I want to make sure you see why. What I'm going to do is I'm going to take this equation and I'm going to use the rule for capacitance. Okay, capacitance is is equal to Q delta V. So Q is equal to C delta V. Yes? So if I take this equation and plug it each in here, Q total would be C total times V total is equal to C1 times delta V1 plus C2 times delta V2. Yes? And what did we just say about all of the V's? So the total, so that would cancel those out. So the capacitance total is equal to the capacitance of the first one plus the capacitance of the second one. Meaning, if the first one stores 10 microcoulombs per volt, and the second one stores 2 microcoulombs per volt, in total we would expect them to cover 12 microcoulombs per 1 volt. So you're seeing hopefully here in these numbers the exact same thing we just said. Hey, if the charges all add up to the total, then for the same voltage, if this one stores 10 and this one stores 2, then in total they should store 12. Does that make sense? So your equations... Well, we're a few steps away from that. Okay, these are the 3 equations. These are the 3 relationships you need to understand. Now, this guy applies to more than just 2. It could be 3, it could be 4. So I'm going to change a couple things about it real quick. I could say, good night, plus C3 plus ... for as many capacitors as there are. And instead of saying total, let's say the equivalent. All right. Now, here's why that makes really good sense for a second when you think about it from this perspective. What did we essentially do by adding another capacitor that's parallel? Well, essentially what we did at the same voltage, like imagine these are the same size capacitor. What we basically did is we just took this area and made it twice as big. So by giving it a lot more area, we give it a lot more room for charge, and we can store a lot more charge for the same voltage. Why is this particularly helpful, Spainhour? Well, sometimes, rather than get a giant-ass blue one, perhaps I can get 2 that are much easier and fit into my device that are smaller, but literally by putting them in parallel, I can get the exact same effect as a larger one for a smaller amount of space. Next. What if instead I hook it up like, let's actually start with the same color that we did last time. I've got my battery and I hook them up like this. This is what is known as series. And unlike the last one, which is multi-paths, 1 item down each, this is 1 path, multiple items on each. Now, this one's harder to see. This one's harder to see. Because here's the truth. The total of this up here is still going to stop. The total... oh, darn it. Come on. Move. Move. Okay. When I say the total, I mean the whole of this is going to stop when the voltage across each is the same. Except the voltage from here to here and here to here are not going to be the same. If you will, you can kind of think of this like, oh, I got you. This is great. This is great. I'll use my hill analogy. When I said it's parallel, parallel is like running 2 hills next to each other, right? You can have multiple kids going down each. But this right here is saying, let's stack these hills on top of each other, okay? Is the same power source in total is going to get the same amount of kids to the top, But is each hill going to get the full amount of energy? No. Now, we are still going to get the same amount of kids to the top. So, hardest one to see. Took me forever to figure this out, so I'm just going to give you the rule. It's this. The charge that would normally be stored in a single capacitor here, wrong side, minus Q plus Q, is also the exact same amount of charge that will stored on all of these. Minus Q plus Q minus Q plus Q. The problem is that each capacitor is going to use its own particular amount of voltage. So here's the relationship. The charge in total, like it would normally be here, this charge total for a single one, is equal to the charge stored in 1 and the charge stored in 2, meaning whatever charge is here and is also here, if I call this capacitor 1 and capacitor 2. But the voltage is split, meaning the voltage total is equal to the voltage of 1 plus the voltage of 2. So if I go back to my analogy, the first statement says I'm still going to be able to store the same amount of kids on top of that hill. But the second statement says those hills are now stacked on top of each other. So each individual hill is going to get a little bit less of the voltage relative to if it was by itself. Now, what effect that has is this. If I go back to this equation that we did earlier, and I do algebra on it, I get this. Delta V is equal to Q over C. We see this? Just basic algebra here. And now I'm going to plug in here. This is Q total over V total is equal to Q1 over V1 plus Q2 over V2. And what is true of, I'm sorry, I did that dumb. It's meant to be C total. C1, C2. And what's true of all of our Q's? So they cancel. Giving us the other new relationship for parallel is 1 over C equivalent Now, you would like to believe, you would love to believe that this equation here is just the same. Why is that not the same as adding them all up? And it definitely isn't, because of basic rules of fractions. As a matter of fact, here is your general rule. Actually, before I get to that general rule, let's just remind you of this. Basically, putting them in series goes back to this equation here. But instead of making area bigger, what are we making bigger in this case? Distance. And like last time I said, if I double area, I double capacitance. Here I'm keeping the area the same. So what is increasing distance going to do to capacitance? Decrease it. This is a way to actually decrease the capacitance of multiple capacitors. And there's other values to it that we're not going to worry about right now. All right, here's the general rule. Capacitance in series will decrease. Or in other words, an equivalent capacitor is always smaller than the smallest individual capacitor. The equivalent capacitance is always smaller than the smallest capacitor. And if you go back a slide, the opposite is true over here. In parallel, the equivalent capacitance is always greater than the largest. Now, in this case, I think everybody can go like, yeah, Spainhour, well, duh, that's how addition works, right? If this is 6 and there's anything over here, what this says is equivalent will be bigger than 6. Okay. So let's just practice real quick. Let's say I have 2 capacitors, one of which is 2 microfarad and the other is 4 microfarad. Okay? Calculate for me real quick, what is the equivalent of the two of them using this right here.
One point.
3 over 3 repeating, yes. So if you do your fractions here real quick, it's 1 over 2 microfarad plus 1 over 4 microfarad. But don't forget that the result is also inverted. So just doing math real quickly, if you want to in your head, you have to find common denominator. So this is 2 over 4, 1 over 4, which means 1 over C is equal to 3 over 4 microfarad. So to get C, then you have to invert at the very end. C is equal to 4/3 or 1.333 microfarad. And again, you'll see that this math does match with what I said earlier. The smallest is 2. The smallest is 2, and therefore the equivalent will always be lower than the smallest. Does that make sense? Okay. Now, great, Spainhour, how am I going to use these? How am I going to be expected to do these? What you're going to get is you're going to get a system of capacitors, okay? So you're going to get problems that look like this. You're going to have like a battery here, and then it'll say a capacitor here, and a capacitor here, and a capacitor here, okay?
Would you mind using one directly from the remote?
I would actually, yes. I want to do these like brand new, so you can kind of see the ideas of this, so I know I can control exactly what the numbers are and that type of thing. Okay, so let's go ahead and say let's just do what we just did. Let's say that's 2 microfarad. Let's say that's 4 microfarad. And let's say this one over here is 3 microfarad. Okay? And then I have, let's say, just a 10-volt battery over here. What you're going to be asked to do is you're going to be asked to figure out regularly the following questions. How much charge is on a capacitor? Okay? How much voltage is on a capacitor? And how much, most importantly, energy is stored on a capacitor. Now, here's what you have to do when you're looking at that. Are those 3 in series or parallel?
The top two are in series.
The answer is yes and no. Correct. The top 2 are in series.
But
The
they also
sort of, okay? Remember what I said about parallel. The ultimate answer is parallel is like a path. Like basically you could say these 2 paths are in parallel, but you'll remember in order to use that equation, I specified that parallel is multiple paths, 1 item on each, right? So if you go to my picture here, is there only 1 item on each of the paths? No. So here's what you do. Okay, and I expect this extra work. It's going to seem like extra work, but I don't care. Every year it helps. Trust me, trust me, trust me. What you're going to do is you will find equivalent and you redraw. Okay, in this case, you can redraw. We've already done this one, so we don't need to worry about doing it again. So I'm going to redraw. Here I have 10 volts. We know that the equivalent of a 2 and a 4 is 1.33 microfarad, and you would have to do the work just like we did just a second ago. Yes? So you guys understand how I got that?
yes.
It's literally what you did just a second ago. They are in series, so you had to do this. You would have to do this right here. Okay? Now, are the remaining 2 now in parallel? Yes. So what do you do to get the equivalent? You're just going to add them. Okay? So I'm going to do that work, and I'm going to redraw. And I end up with 4.33 microfarad, and there it is. Once you are at a single capacitor, instead of, so this is an equivalent capacitor. Like if I said, here's what I would regularly do. I'd probably call this one, well, I've already got numbers. I was going to say 1, 2, 3. We've already got numbers, 2 and 4. So this is capacitor 2, and this is capacitor 4, and this is capacitor 3. Then this equivalent here is capacitor 2, 4, the combination of all of them. Once you, sorry, of the 2 and 4. Once you have all of them together, this is capacitance total. Once you have capacitance total, what you can do is you can use your equation for capacitance and figure out how much, well, for sure not figure out, how much voltage is on that. How much voltage would be across this capacitor once it's fully charged?
10?
10. Yes. Remember the...
Oh, because when it's
Yep.
fully charged. Okay.
Once it's fully charged, the voltage here will be the voltage across there. So what I can do is this. Watch carefully. I can find the charge total is equal to capacitance total times the voltage total. Or 4.33 microfarad times 10 volts says that the 43.3 microcoulombs will be charged in total.
So why is it now CT instead of CEG? Are they interchangeable?
Do what now?
Different? Why is the capacitance total?
I said that.
Now?
So it's total once you are at a single equivalent resistor. There are no other. This is all of the capacitance wrapped up into one. So if you want, capacitance total is an equivalent capacitor of 2, 4, and 3 all combined together once it's at its very end. So this is why earlier you saw me kind of go interchangeably between total and equivalent. All right, now, again, what you're going to be asked on the regular is, okay, what's the charge? Great. What's the charge and the voltage across each capacitor? So the general steps are, watch here carefully, I'm going to break them down again so you can always hopefully follow them. 1, draw your original picture. Then start redrawing using equivalent resistors to break it down simpler and simpler until you're at a single capacitor. Once you're at a single capacitor, using the total voltage and the total capacitance, you can get total charge. Now watch this. To get the capacitance and the voltage on each of these, what we're going to do is we're going to work our way back through the pictures, okay? And we are going, excuse me, to use the rules that we talked about. So this guy right here replaces these two. Yes? Look at the relationships. What are the relationships that are the same? What is the same for this that is the same for both of these two? Well, this is in parallel. So I go back. I look at my relationships. What are my relationships? That's the things that I highlighted with the boxes here. So what is the same for the total as is the same for both of these two? Voltage. So, do I know the voltage across that guy? What is it? 10. So do I know the voltage for both of these? It's 10. So can I find the charge on both of those? Yes. To find this one, I'm going to say the charge on 4,2 or 2,4 is equal to the capacitance of 2,4 times the voltage of 2,4, or 1.33 microfarad times 10 volts, 13.3 microfarad. The charge on the 3 is simply equal to the 3 microfarad times 10 volts is equal to 30, oops, sorry, I screwed this up over here, this should be coulombs. Microcoulombs. And look at this. What should also be the case? Well, we learned over here that what should also be the case is the charge on both of them should add up to the total. Does it? Well, the charge on this one's 13.3. The charge on this one is 30. And what was the total charge? 43.3. Is that the same? Yes. So do you know, for example, on this capacitor, do you know how much charge is stored on it? Yes. Do you know how much voltage is across it? So if somebody asked you instead, what's the energy on that capacitor? The energy stored in a capacitor is 1/2 Q delta V. So you could take 1/2 times the Q of 30 microcoulombs times the voltage of 10 volts, and you'd end up with 150 microjoules.
Wait, where'd you get that equation from again?
This equation is the third equation that I talked about it last Friday. I didn't review it again today. This is the amount of energy stored in a capacitor. Now, let's go back one step further. The whole idea on this was that we know the voltage and we know the charge in every capacitor because that would allow us to get energy. We know this one, right? We're just working our way back. Now, notice that this capacitor is now these. What is the same for both of these, for this one, as it is for both of those? What is the... Oops, oh, too far. What's the same? Sorry, I'm kind of, hold on. Let me make sure to highlight these relationships the same way as I did the others. No, voltage was the in parallel. In series, what's the same? Charge. In other words, I know that on this one there is 13.3 microcoulombs. So I know here there is positive 13.3 microcoulombs, negative 13.3 microcoulombs, positive 13.3 microcoulombs, negative 13.3 microcoulombs. But will they have the same voltage? No. So I take my equation for capacitance. The equation for capacitance basically does this. This says, watch carefully. If you know Q and C, then you know delta V. If you know delta V and C, you know Q. That's the one we used last time. So here we go. I'm going to rearrange this because I want to know. I want to know the voltage across each of them. So voltage is equal to Q over C. So what is the charge stored on this one? What's the charge stored?
Would it be 10 over 43.3?
And that's going to be the 13.3 microcoulombs here. Capacitance is 2 microfarad. That would be the voltage of 2. The voltage of 4 is going to be 13.3 microcoulombs divided by 4 microfarad. And here you get 6.65 volts. And here you get 3.35 volts. You'll notice this is pretty darn close to this. That's about twice as much as that. And what should these add up to? 6.65 plus 3.35 better add up to 10, which is exactly how much voltage is across there. Let's give you another one to practice. But essentially, if you can do the problems that I'm showing you right now, you should be able to do pretty much everything on the homework.
Oh my gosh. I think I did it, guys. I think I'm done for the first
I was one of the simple numbers that I can help with, but I want to. Hold on. Let's go 4 to 1. Yeah. Let's do 20 and let's do 10, 30, and 160 over here. And once again, for the sake of voltage, let's just go ahead and make it a simple 10. That's not normal. It should be like, normal should be like a 12 or a 120 in that particular case, but let's just keep the math easy. All right, so what's the first thing you should do? We want to find the voltage and the charge on each capacitor. What's the first thing you should do?
So, would I be correct in saying that the two capacitors that are on the right, that are right above each other, are those parallel?
Mhm.
Okay. So, I would add those up and then have it be.
Okay, do that and redraw.
Yeah.
Do that first.
So then you have two of them in series next to each other.
Correct. So what you should have now, if you've done it correctly,
Is that one on the left 160?
it is. So what should the total capacitance be of this cell?
Can we move it back over? Over just a little, or never mind, I can see it, it's fine.
Could you tip the board a bit?
All right, what's the total capacitance?
32.
32. How do you do this one?
Since they're in series, it's 1 divided by. Okay.
Now, what people screw up regularly is they'll do this side and then go, oh, I'm done. But keep in mind, this is not the answer yet until you invert it. If you prefer, some people do like this instead. C is equal to all this to the negative first once you're done. That's also completely fine if you'd like it like that. And if you do that, you should end up with 32. All right, once you have the total, what do? Now you've got the total. What did we do once we had the total last time? First thing you're going to do is find the total charge. And you're going to do that with Q equals C times V. Total Q, total capacitance, total voltage. So capacitance is 32 microfarad, voltage is 10. How much charge is stored? 320 what? Nope. Microcoulombs, because of the micro there. So on the last problem, just to highlight what we did last time, so you can hopefully see it, the exact same thing as before. Broke it down, broke it down, broke it down until the very last picture here, and then we found total charge. Now listen carefully to what the next step is. The next step is work your way back. There is a reason you draw these pictures in this order, okay? Basically, right now you can think of it like this, okay? If we made like a table, some people like a table here. To help, you need total capacitance. Total capacitance will give you total charge. Then the goal is to find the charge on every capacitor and the voltage on every capacitor. If you set up a table like this, the nice thing about that is that once you know one of these through capacitance, you automatically know the other, because capacitance is the ratio of the two of those together. Okay?
So you get C total to get Q total, and then from Q total you can get Q1, Q2.
Well, not necessarily. You can't necessarily just go straight down. It depends on the relationship. Over here, here's what we did, this last problem. What we know is we know the Q and the delta V on this equivalent capacitor. And an equivalent capacitor, by definition, has the same total Q and the same total V as what it represents over here. So what I asked you to do is I said, look at your relationships and which of these two numbers, totals, is the same for each of these. Now, ultimately, both of them. But here's what I was saying. In parallel, the voltage total is the same as each individual voltage, where the total charge is split. Right? So, when we did that problem here, we said the 10 volts that's on this guy will also be the 10 volts here and the 10 volts there. The charge is also in total the same, but some of it is here and some of it is there, and we don't know how much. So we used the voltage along with that capacitance to tell us how much charge is on it. And we use the voltage again along with this capacitor to tell us how much charge is on it. And this told us what we saw before, that the Q total is equal to Q1 plus Q2. So what you do is you look at the picture, okay, and you say, all right, on this 32 microfarad, we know the total voltage is what? 10 volts. Okay. The total charge is what? 320 microcoulombs. What you have to do is go, okay, this represents these two. So what is the relationship that is the same? Which of those numbers is going to be the same for all of them? Charge. If you don't have these written somewhere on your page or somewhere where you're like easily looking at them every time, you're shooting yourself in the foot here, because I would imagine those are not naturally coming to your head. So what can we do? We know that the Q on this one and the Q on that one must be 320 microcoulombs. Yes? So what can we do with that? Well, we know capacitance. So, watch here. Just me doing algebra every time. Delta V equals Q over C. So the Q, 320 microcoulombs. And the C for the first one is 160. You could probably do this one in your head. 320 divided by 160 is 2 volts. And that would be for the 160. The voltage for the 40 is also 320 because the charge is the same, but the capacitance is now 40. And I get 8 volts. Here's why that makes sense. What should the individual voltage of each of them add up to be? Not around, ideally, exactly. So what was our total? 10. 2 plus 8 gives us our 10. So now, you know the voltage on each of them. The voltage on this one was 2 volts. The voltage on this one was 8 volts. And you know the charge for both of them, 320 microcoulombs, 320 microcoulombs. This is an actual capacitor. This one's an equivalent. So for the equivalent, we have to step back again and say that this is this one right here. So now, what number is the same for both of them?
Since they're parallel, it would be the voltage.
Voltage is the same. So like no, so what's the voltage on both of them then? What was the voltage on the 40? 8. So the voltage on both of these is 8. And once again, C equals Q over delta V. So Q is equal to C times V. The capacitance of the first one there is 10 microfarad. The voltage is 8. So this capacitor, the 10, stores 80 microcoulombs. The charge of the 30 is equal to that 30 microfarad times 8 volts, which gets me 240. And once again, what's 80 plus 240 equal? Which is exactly the total that we said a minute ago over here. Now, if any of these, and they regularly will ask you how much energy is being stored here. Here's a homework problem that is, it's way, it's a lot more complicated than I think it at first looks. It'll give you a setup like this, and it'll say, hey, how much energy is being stored here? Now, to get energy, what do you need? Exactly what we've been finding for everything, Q and delta V. So you might well be like, oh, I can go straight there. No, you really can't. What you have to do in this particular case is you have to do exactly what we just did. You have to break this one down to this one to this one to get the total, to work your way back, to work your way back. Now, I will tell you this. If it wants to know this one in particular, there's some extra work here that's like you don't need to know anything about the 160 in this case, and you certainly don't need to know anything about the 10. You could just kind of work your way back one at a time. But then, to figure out how much energy is stored on that capacitor, we would take 1/2 times the charge stored on it, 240 microcoulombs, times the voltage, 8 volts. And that would be what? 120 times 8. So 800, 160, 960 microjoules. That's it. That's all the new stuff.
Tutoring tonight, right?
Yep, I got a lot of people coming in for a lot of different reasons, as a heads up.
Oh boy. I already have all my hours. I'm just there to work. People
Fair
need
enough.
help, then I can, but don't need no hours.
So what homework problem do you want me to look at real quick?
Let me see.
I actually can't think of any.
What's that?
I actually can't think of any.
So,
I'd imagine they double up. Just tell me what both of them are, and we'll see if we can't double up here.
823 and
Well, I'm
pretty
referring
sure
to
16
capacitance problems right now, so I'm not going to do 8. Sorry, go ahead. 23 and...
And I feel like now that I've done it, I think 16 through 18 I can get. So how about 20?
This is not a capacitance problem. This is literally just,
I
that
know
is
it.
the... What's
There's
that?
a question that
Okay.
I couldn't do.
Oh, gotcha.
20 is one that would be nice. It's more of just I tried doing these before we had this
Sure.
from the textbook and I don't really understand.
2 capacitors, 22 microfarad and 42 are connected in series. A battery. Yeah, man, it's actually even easier than what we just said.
Okay.
Because
I feel
it's just and all right, based on what we just did. Here's what that was. That was just, hey, there's 2 capacitors connected in series. So find the equivalent of both of them, and then just work your way back just once, as opposed to 2 or 3 steps.
All of the ones that I had questions about now, because they all dealt with that. Besides 23, but you just said capacitance ones.
23.
Just I tried it a few times, and I feel like the way I'm going.
Small object with a mass of 310 micro carries a charge and is suspended between a thread of pearl plates. The plate is separated by 5 centimeters. If the thread makes 18 degrees, what's the potential difference between the plates? Okay, so here's what you should see based on this. That looks very complicated, but I will give you the equation that you really need to help you out here, and it's this. Delta V equals A times delta D. The problem straight up tells you the distance between the plates, right? So what I would say to you is go find electric field.
And so I did electric field equals force electric charge.
So you should have, hold on, let me make sure. Suspended by a thread between 2 vertical plates of a capacitor. So yeah, it's just, let's make sure this is the right setup. But here you go. Positive, negative. There's a thing going this way. The object is right here. Tells you the angle with the vertical. So the force doesn't matter. Force, gravity, tension, force, electric, exactly like problems from last chapter.
Yes.
Keep in mind, force electric, since this is a uniform, is just QE, right? So this is going to end up being sum of forces in the y equals mass times acceleration. That's 0. Force tension in the y is going to equal mg. Okay. Sum of forces in the x equals mass times acceleration in the x. There is no acceleration, so force tension in the x is equal to QE. Okay. When I look at my angle is up here, it's 18 degrees. Force tension in the y, force tension in the x. So tangent of 18 degrees equals opposite force tension in the x over force tension in the y. So force tension in the x is equal to, this is just mg via that, times tangent of 18 degrees. And based on that, it's also equal to QE. So E is equal.
So I did tangent theta mg over q, except whenever I guess I did something wrong whenever I put mine in.
I mean, make sure that says that's microkilograms.
Yep.
So that should be times 10 to the negative
okay,
6.
So I did the process right. I guess I'm just going somewhere wrong.
Yeah. That's negative 6. That's negative 9. Centimeters should be in meters when you do it.
Yeah.
So that should be 0.05. 18 degrees. Yeah, you have everything that you need there. So this will get you.
Because when I solved for it,
this should get you E. Once you have E, it's literally just this right here.
I think I may have forgot to do that.
That'll do it.
Oh, that's funny. Oh, that's horrid.
So mass is 310 e to the negative 6 times 9.8 times the tangent of 18 degrees divided by the charge, 25 e to the negative 9th, gets me an electric field of 39,484 times the displacement between them, which is 5 centimeters or 0.05 meters. I have 1,974, so I'm going to put 1970.
I'm going to be so upset if this is correct, because there's no way I tried this many times and all I was forgetting was to do the final step. Let's see.
I am incorrect. Let's see.
I am also incorrect. It says I differ significantly.
Say 18 degrees of vertical. Ah! That's exactly what it is.
No. And like
That says grams.
Uh-huh.
Did you not do that?
They all need to be converted.
To kilograms.
Yeah.
So that should be times 10 to the negative 9th then?
I think I did. Oh no. Oh no. Oh no.
Negative 9.
Hold on.
Oh yeah, no, I knew.
I think that's weird.
So I'm going to divide my answer by 1,000. 1.97. Ta-da. So what I did is I punched in 310 times 10 to the negative 6th, which is micro, times G, except that's grams times G, which does not give you newtons. So I needed to go 310. What's that?
Can I see your numbers? It's real small. I'm sorry. Just maybe. And so you said you got. Hold on.
So what I did is I took, like right here, it's the same work. It's not wrong. I just punched in 310 times 10 to the negative 6th. Well, that is correct if I want to go to grams. But I don't want to go to grams. I want to go to kilograms. So this should be 310 times 10 to the negative 9th kilograms.
Okay, let me try this and see if it works now.
You should be able to, if it does work, you should be able to take your previous answer in the 1,000 and divide by 1,000.
I kind of scratched out because I thought the entire methodology was wrong.
Cass, you asked about 8.
Yeah.
Did it work?
It's just like algebra, and I say, yeah, I don't know what I did.
Symbolic expression for the total electric potential at the center of a square by 4 charges. Well, each of them is going to be that kq over r.
Yeah. It's gonna be 4K.
Now, if it's a square, your biggest issue is that you're going to run into your distances. I think all of them have a side of A. So let's see here.
Yeah.
4-point charges. So it's this. Okay, but it's asking about the center, right? So to get that distance, if all of these are A,
You gotta do the thing.
you'd go A over 2 to get here, but that would be squared plus A over 2 squared square root, and you'll end up with A over 2 times square root of 2.
That might have been it. I knew there was
Because this is the distance you want. So you can do Pythagorean theorem, and this should be A over 2 times, square root of 2. Then what you'll end up having is you'll get an individual K is just the charge. Well, no. That was dumb. Individual potential is K times the charge over that A times square root of 2 over 2. But there's 4 of them, so literally just take that times 4.
I
Now,
did that, but I think I just did I just upped the square root of the 2 somewhere in the word.
sure. So when you do this, though, simplify this fraction on the bottom. I think it's going to end up as K times Q times 8 over square root of 2A, if I'm not mistaken.
Okay.
But we
Thank
can
you.
look at that again tomorrow if necessary.
Yeah.